Hello and welcome back. In this lecture, we discuss about variation of pressure in a static fluid. To better understand this concept, let us quickly review Pascal's law discussed earlier in video 16. We have seen that a force applied on the piston generates pressure inside the fluid. Assume that the fluid is static. That means it is stationary and not flowing. We have discussed the meaning of pressure at a given point in the static fluid in this example. To better understand this, consider a differential volume element of air, within the continuum approximation. Imagine that, air surrounding this volume element, exerts force on each side this element. This force per unit area, is the pressure exerted by the fluid on this imaginary, static fluid element. Since the element is in static equilibrium, we can show that the pressure acting on this fluid element, from all surrounding direction is same. That is, pressure at a point in a fluid at rest, is independent of direction. This important result is known as Pascal's law. Although pressure acting at point, in a static fluid is same from all directions, it will change from one point to another. We will see how this variation of pressure happens in a static fluid. Consider again a fluid element in the previous example. The forces acting on this element are the pressure forces from the surrounding and the weight of the fluid element. It can be shown mathematically that for a static fluid, pressure varies only in the vertical direction, and remains same at same horizontal locations. In this case, pressure at location 3 is same as pressure at 1 and it is different at location 2 at a different elevation. Consider a fluid with free surface, say water. Let us see how pressure varies in this static fluid. At location 1, the interface of fluid and atmospheric air, the pressure is atmospheric and let it be P1. This is approximately equal to 101 kPa. We have seen earlier that pressure varies only in the z direction in a static fluid. Since the pressure changes in z direction, this equation can be integrated from one location to another. Finally, we can derive an equation that connects pressure at the free surface to a different point in the fluid at a depth of h as P2 equals P1 plus ρ gh. Consider a practical situation. Water is stored in a dam as shown in figure. Calculate the pressure at 3 different locations. We know that pressure at location 1 is the atmospheric pressure. To calculate pressure at a different location, we use the equation derived earlier. Using this equation we can calculate the pressures at depths 25 meters and 125 meters. Assume the density of water as 1000 kg per meter cube. Average ocean depth is approximately 4000 meters in the Pacific. The deepest place is 10,000 meters down the free surface. Calculate pressure at these depths. Assume atmospheric pressure is 101 kPa. Density of seawater is 1.2 kg per meter cube. Using the previous equation we can find the pressures at these locations. Note that the pressures at these locations are dangerously high. Imagine that planet Mars's atmosphere extends 8 kilometers from its surface and the average density of atmospheric gases is 1.5 kg per meter cube. Calculate the pressure at the surface. We will solve this problem in class. Finally, here is a summary of the key concept of this video. The pressure at a location, in a fluid can be related to the pressure at a reference location in the fluid, density of fluid, gravity, and the distance between the two locations. Thank you for listening. Welcome.